Okay, I think we are now live. Okay, let me share my screen first. So yesterday I was not able to solve a problem. Means we were able to implement its brute force approach, but we failed into optimizing it. So let me first share my screen. This one or this one. Okay. Okay. So yesterday we were solving this problem. Reconstruct itinerary, and we have coordinates this solution. We saw that there is a concept related to this problem, Eulerian circuit. Okay, so we do have one more good problem on this. Valid pair of. Okay, so we have how many problems left? Around 60 problems left to solve. So today we will do this problem, reconstruct itinerary. So this was the approach we were using yesterday. So before solving this problem, we will solve a similar problem to this, which is a valid arrangement of pairs, which is this problem. So to these both problems, there is a concept which is common, which is Eulerian circuit. Here we go, Eulerian circuit. So we can look for this topic on Wikipedia or Gigs for Geeks. So basically, what this means is for directed acyclic graphs, directed cyclic or acyclic directed graphs, we have, suppose we have this particular array, and we need to return an arrangement such that suppose this arrangement is start ends from 9, so the next pair to it should start from 9, and it is ending at 4, and its next is starting from 4. It's ending at 5, it's next starting from 5. Okay, so suppose we can consider these numbers as nodes. So 11 as a number, 9 as a 11 as a node, 9 as a node, 4 as a node, 5 as a node, 1 as a node. So how we are returning? We are returning 11 to 9. That first we will go 11 to 9. Okay, then we go to 9 to 4. Then we will use this as 9 to 4. Then 4 to 5. So then we will use 4 to 5. And at last we are using 5 to 1. So this is a directed edge, directed acyclic edge. Now let's see this second example. So for this particular edges, we have already these edges aligned the way we need it. We need arrangement like 1 2 3, then the this is ending at 3, then next should start at 3, so this is starting at 3, next ending at this ending at 2, so next starting at 2. And one more thing we can see is suppose we have these nodes 1 2 and 3. So what we are having first, we are going from 1 to 3. Okay, so we can have a other arrangement for this also. Okay, so what we can do, from one node we can go to the 3 node, and from 3 node we can go to the 2 node, and here from 2 node we are going to the 1 node. Means we also have a reverse edge here. So basically this is a cyclic graph. Means we can have both inputs, cyclic or acyclic graph. And the question says we need to use all these edges, and there always will exist an answer. So we need to use all edges, and there exists a answer. So every time there will be an answer, and we need to use all these edges. Okay, and we need to return a valid arrangement like this. Okay, so we have nodes for let's say for this cyclic graph, we can start from any node. Means we can let's say we have these 3 nodes, 1 2 3, 1 2 3 edges. We have 3 to 2 and 1 to 3, 3 to 2 and 2 to 1. Okay, so we can start from any edge. I think let's say we start from this particular edge. We start from 2 1. Then we can we need a edge which starts with 1. So this edge starts with 1. Okay, 1 3. Now we need a edge which starts from 3. So we have a edge. So in cyclic graph, we can start from every graph to transverse all the pairs. But in this particular graph, this is not a cyclic graph. We need to find a node from which we can start. Means from which we can start transversing. So if we create a graph for this particular node, we have suppose we have 5 5, from 5 we can go to 1. Then we have 4, from 4 we can go to 5. Then we have 11, then from 11 we can go to the 9, and from 9 we can go to 4. So one thing we can see here is from 1 we cannot go anywhere. Means in order to transfers this whole graph over this particular pair should be at the end, because from one we cannot go anywhere, means we don't have any out degree for one. Okay. And one more thing, we cannot come to 11 by any node, means we cannot, for example, put and in between, means this particular edge in between or at the end of the array. So basically we have two definitions. One is we have Euler path and one is circuit. So for this particular thing, we have all the nodes have same out degree and in degree. So that's how it will form a circuit. Means this particular example where we have a cycle present, this is a Euler circuit, and this particular example which is acyclic, this is Euler path. So for Euler path we have a definition that at least one node should have out degree greater than in degree. Means there should be one edge going out from a node uh, than the incoming node, so greater than in degree. And we have a node, one node should have and other should have a reverse of this condition. So for this particular example, we have a 1. So one's out degree is 0. 1 only has incoming edges, which is 5. 5 to 1 we have edge. So one should be, so this, for this condition, this node should be present at the end of this transversal, and this node should be present at the start of the transversal. Basically we need to find Euler path or Euler circuit in the example, in the question. So first we will check whether our graph is a circuit or a path. For a circuit, we can start from any node. For example, here we can start our this particular what we can say arrangement from any position, and we can get a valid arrangement. But here we carefully need to decide that from which node we will be starting our transversal. So we need that node first. So first we will create a graph using these edges. Okay. So we need a list of integers to store neighbors. Okay. New hash map. We now iterate our pairs. So this is our current pair in the iteration. So what we need to do, we have a from position that we need edge from this position to this position. Okay, we will put this edge graph dot compute if absent. So this will check if our list is present at this from position. If it isn't present, we will insert an empty list of neighbors. and this function will return us that list if it is present the list with the neighbors, otherwise a empty list. Then we will add 2 as its neighbor. So this is our directed graph. Now we need to calculate the in degree and out degree for the nodes. So one thing we can do is we can calculate in degrees and out degrees uh, along with the node, I think. Can we do it? Okay, we have a graph, integer, neighbor. Okay, we can also store in map the out degree and in degree. Okay, we can, what we can do, can take this as a other data structure in which we can put a list and in degree and out degree variable. Or we can just create a separate array for now. So this will store degrees and its size will be, so initially we don't know how much uh, nodes we can have graph. So we need a list of integer of degree for storing degrees. Basically it's a vector of vector. Now we will transverse our map. Okay, so fitted graph in degree out degree. When we need to again, okay, we can transfer our pairs and put in degree and out degree. Okay, we will use this to store the in degrees and out degrees node data. Okay, so it will initialize with these values 0 and empty list. Then we will transfer our pairs, and we will check if our graph dot get, or we can check if our graph contains key from, then it already have this node data. So let's initialize node data, current data. So graph dot contains key, then we will get its node data if we have already initialized this. So current data will be graph dot get from. Okay, otherwise we will create a new data, new node data. Okay, and what we will do, we will, this is for the from part. Okay, so we need to increment out degree for from, that we are having a node from, and we need to increase in degree for this two node. Okay, first we will do it for node. So what we will do, this current data out degree plus plus, we have increased its out degree, and into its neighbor, what we will add, current data dot neighbor. So this is the list neighbor dot add two node. So we have added a two node to its neighbors and increase its out degree, and now we need to uh, increase two nodes in degree. So what we will do, we will see, uh, we will do something similar. So let's say this from data, this is the data for from node, from node, and this is the data for two node, two data, and we can put two here, and two data dot in degree. Now we don't need this thing. Okay, so what we have done here, for a particular node we have stored its neighbors and its out degree and in degree. Now we need to transverse this graph and need to check for which node we have out degree greater than in degree, means from which node we need to start. Let's iterate this graph. So this is a way to iterate the graph. So we will get the entry of the graph, that what type of entry our graph contains. So our graph contains this type of entry. We will call current entry as en, and we will get all the entries of the graph entry set, basically all the nodes present in the graph. So our, what we need to find, we need to find out degree and in degree. Okay, so suppose, so how we can, why we need these degrees? So we need to start from a node. Means in the cyclic graph, we can start from any node. And one thing we can be sure about is that for cyclic graph, every node will have in degree and out degree equal. So these conditions will not met for a cyclic graph. So in cyclic graph, we can start from any node. So initially, suppose we have cyclic graph. So let's say we start from this node, the very first node in every pair. Pairs 0 0, and now we look for the values. If we have any node for which out degree is greater than in degree, then that node we will replace, start with that node. Okay, okay. So our current node will be uh, entry dot get value. So this is our current node, and our node data will be current data, which will be en dot get value. So we have this key value pair entry, and we are just checking, just getting its value. So this will be get key not value. So we will check if our current data's dot out degree, if our current keys out degree is greater than dot in degree, then we can replace our start node with this node, and we can break. So only one node will have out degree greater than in degree in is this Euler's path. And in Euler's circle, all nodes will have same out degree and in degree. We can choose any node to start from. So we are taking this as the default node in the case of the cyclic graph. So now we can check if we are getting a correct start node. So this is all to find the start node. Okay, let's print this out. Start. Okay, and at the end we need to return something. So we will return a, let's create a, let's return an empty array. Okay, so let's check our code first. So we have created a graph with node data and graph. So node data will include out degree, in degree, neighbors. Initially out degree, in degree will be 0, neighbors will be empty array list. Then we will iterate over the pairs. So current pair from will be this, to will be this. Now we will check if this pair already exists. This key is already is in map. If our graph, if graph contains this, we will put it into from data. Otherwise we will create a new node. We will add to its to neighbor, increase its out degree. Okay, we will increase its out degree, and for two node we will increase its in degree. Okay, then we are assuming in the cyclic graph very first node as the start node, and then we will look for a node in our graph which has out degree greater than in degree, then that will be our start node. Okay. Okay, we are not having these variables. Okay, so this will be not current data, this will be true data. Okay, and here we need current data. Okay, or we can call it as node data, or simply as the data. Okay. Okay, we need to make this I smaller. Okay, so for the first graph, our start node is 5. Okay, so I think even if we, as this graph is not cyclic, so is even if we change this order, uh, output will be 5. Let's make this order. Okay, now we are getting 4. It should be 5. 5 or what's in the, it should be 11, because 11 has out degree greater than in degree. We are getting this only, means we are not having a condition where this particular thing satisfies. So can we see what our graph holds? Like we can print this node, and along with this node we can print its neighbors, which will be data.neighbor. Print ln. Only getting this 4. Okay, one thing we are missing is we need to put this thing into graph. Otherwise, how we will gonna get it? Graph dot put from node, and from node we will putting from data. We can remove it from here and put it at the end. So we need to add data also to the graph. So this is the separate part. Okay, so our one node has no neighbors. 4 node has 5 as the neighbor. 5 node has the 1 node as neighbor. 9 node has the 4 as the neighbor, and 11 node has the 9 as the neighbor. And we can see that our start node here is 11, I think. Our start node is 11. So we need to start our sequence from 11. Okay, so as we can see, the sequence is starting from 11. And we can say for other test cases also, sequence is starting from 1, because this is a cyclic graph, so it doesn't matter from which node we start. And this example we are starting from 1. I think this is also cyclic. From 1 to 2, 2 to 1, 1 to 3. This is also cyclic. So we can start from any node. So we are picking up first node. So now we have start node and we need to transverse this graph. Basically now we need to find a topological sorting for this graph. Means topological sorting, what the definition of topological sorting is. So in topological sorting, if we have means u node comes before uh, v node, if we have a edge between u to v, where is v? We can, so basically topological sorting for directed acyclic graph is linear ordering of vertices such that every edge uv, the vertex comes before v in the ordering. So we need to find a topological sorting of this particular sequence. Wait a second. Okay, so we have found the starting point for our graph. So now just we need to the inputs are generated such that there exists a valid arrangement of pairs. Okay, so we just need to transverse our graph, means from one point we need to go to another point. So this is start node, so we need to go to the other point. We just need to find a valid arrangement. Okay, so what we will do, we will have a start node. Okay, and we have our graph. So this is our start node in start node, and this is our graph. What we have copied. So our we need to iterate our neighbors of this graph. From this start point, we can go to its neighbors, which will be we have current data. Let's call it data of the neighbor. So we can take node data. Okay, we need a list of neighbors. So wait a second. So our current neighbor will be neighbor will be this current data dot neighbors listing. Okay, so this will give us a neighbors list, and this will be our current neighbor. So we will go to this part. So basically we need to implement we need to find a topological ordering of nodes in our graph, so that will return us this sequence. And also we need to store our answer. So in topological sorting, what we can do, we can pass a stack of let's say array, because we need array of array as the output. So stack is equals to new stack. Okay. So our current pair will be of two size, which will have a zero value as the start. Suppose we are starting from 5, so the first pair here we will starting from 11, so we start from 11, so then we go to neighbor of the 11 9. So first we will store this 11 means in our current pair, then we need to store its neighbor. So this zeroth value is our start, and the next value will be its neighbor. Okay, so we can do one thing. We can first store the sequence of the nodes which we can visit. Then we can manipulate these pairs. So instead of storing the array in stack, we can store the ordering of the nodes which we are visiting. Then we can create the pair from them. Suppose for this particular example, we will get the topological sorting as 11, 9, 4, 5, and 1. So we can create the above pairs from this particular array. So we don't need, we can just add this current node. So we'll iterate to its neighbor graph and pass this stack, and to the stack we can add our start node. So at the last of the our start this stack, at the very last of the stack means the element will be added after the we have made the successful recursive call. I'm not sure about the order in which we will be getting, either it will be reverse or the correct order. We can, I think, print that. And also for we are not handling case for the cycles, so in the cycles this can get stuck into a loop, so we need to figure out how we can also take care of the cycles. Okay, let's see what our this stack is storing. Okay, so this is called at the last, means after all the calls are executed. So 11 will be at the top of the stack. Means this is at the top of the stack, and then this, then this, then this. Till stack. We need to first run it without the test cases which are having cycles. So okay, for the cycles we need to first remove this test case. Okay, so we are getting this ordering, means one is at the top. Okay, means what is the top of the stack? Stack dot peak. Okay, so 11, yes, 11 has a, is on the top of the stack, so we were thinking correct. Okay, So now we need to find topological sorting for the edges which have cycle. Uh, let's reset our test cases. Test case. With this particular test case means we have a cycle here. So for this topological means for this we need nodes like 1, 3, 2 and 1 in our stack to create the above pair. Means above pair is a valid pair. And for this we need 11, 9, 9 to 4, 4 to 5 and 5 to 1. So for this cyclic part we can start from any node. So what if we remove a edge from the cycle? Okay. Suppose we remove this edge from the cycle and then we transverse. Okay. But for that we need to know that its cycle means this has a in degree, out degree this. Or we can do some modification here also in our this logic, so we don't have to modify the graph. Okay. Topological is working per, we know that topological sort only works for acyclic graphs, directed acyclic. We are somehow need to run it for cyclic graphs also. Then we can have a correct sequence. No, this particular graph is test case test. Not this case. Let's see. This case is not acyclic. This is cyclic graph. We also cannot make a visited node array, means we can visit a node multiple times. Means we need to break this cycle, and then we can have topological sort. 5 to 1. Suppose we have graph like, and then I think it will give us clearly. I have tried this approach yesterday in a similar problem, so I got clearly there. And also, this is the not correct condition, I think, for deciding whether a graph has a cycle or not. We also need to check that one of the nodes should have in degree smaller than out degree. Then only can we say that it doesn't have any cycle. Mhm. To compare in degree and out degree, you need to store in degree and out degree of every vertex. So this is true for a Eulerian cycle. Today I will not forget my charger. Okay, so what are you going to do? That's what I'm thinking. Let's have a. But we can revisit a node. That's the problem. We can revisit a node in this path. Let's say we have this arrangement. From 1 we go to 2. From 2 we go to 1, 2, 3. And from 3 we go to suppose 4, and from 2 again 2, and from 2 we can go to 5. And something like 1, 2, 2, 3, 3, 4, 4, 2, and 2, 5. So here we are revisiting the 2 node. Means we cannot keep track of the visited nodes. And this will happen in the case where we have a cycle in our node. Don't know how we gonna do this. Choose a start vertex V and follow the trail of edges from that vertex until returning to V. But this is for this, it is not possible to get any struct V because given the degrees of all the vertices, there must be an user leaving W, the 4 formed in the way close to one of the vertex and edges of the initial graph. As long as there exists a vertex U that belongs to the current tour, but has an adjacent as not the part of the tour. Start another trial from U, following news edges until returning to U. Our graph can have both circuit and path. So in circuit we have a cycle, in path we don't have any cycle. So here they are only mentioning circuit part, not the cycle part. To compare the in degree, you need to store in degree and out degree of every vertex. Okay, path is returning to us this link. Okay. So this was the problem, the same problem on the same concept I tried to solve yesterday. It is using same concept, the circuit. From this problem I got to this problem, and now I'm stuck in this problem also. Do we have relevant? Could you convert this graph into a problem? Yes, I have converted this graph into a problem. This algorithm, which was discussed in Wikipedia also. I don't have any intuition. I yesterday solved it using the naive approach, using backtracking. So it gave me TLE. Then I looked at the topic. So then I have found that this is a Eulerian circuit. So this is a concept which we need to learn. I think so. Then we can solve similar problems. So to know means whether a graph is Eulerian or not, we can check for conditions something like we need to visit all the nodes and there should be at least one valid answer and some sequence which we need to follow. Here also we need to follow the same thing from JFK, MUC to LHR, LHR to SFO, SFO to SGC. So this is the same question. Okay, given a directed graph path and at the starting vertex. Okay, okay. This is in the sheet reconstruct itinerary. Uh, Reconstruct itinerary, and I am doing this valid pair arrangement. Means both are similar, but this was easy to understand the concept. Problems are exactly same. This I have encountered in a contest before, and then also I was not able to solve it in contest. So there I saw that this uses a concept. So I haven't read the concept at that time. That's why I have to learn it now. Linear time. Below is the Wikipedia. Remember that directed graph has a Eulerian cycle if the following condition are true. One, all the vertices have non-zero degree. Okay, belong to a single component. In degree and out degree of every vertex is same. Algorithm assumes that the given graph has an Eulerian circuit. Means we can make our non-connected graph a circuit. Means we can like this is not a circuit. We can what we can do, we can put a 1 and 11 pair here so that it becomes a circuit. Means then it will start from 11 and end at 11, and then we can apply this algorithm, I think. But may not cover all the vertices and edges of the initial graph. As long as there exists a vertex that belongs to the current tour but has adjacent edges, Start from you, following unsued edges until it returns to you. Long as there exists a vertex u that belongs to the current tour, but that has an adjacent edge, not the part of the tour. Now start another trial from u, following unused edges until returning to u, and join the tour formed in this way to the previous tour. Thus the idea is to keep the following unused edges and remove them when we get stuck. Okay, we will keep the edges and we'll remove once we get stuck. Stuck means the removing the edges which are not part of circuit, but our all the edges, in our case our all the edges will be part of the circuit. Okay, so we don't need to remove any, we don't have any unused edges. Okay, we need to store all the edges. Once we get stuck, we backtrack to the nearest vertex and that has unused edges. We will repeat the process has been used. We can use another container to maintain the final path. Okay, let's start from zero. I think I'm not able to see graph here. There is a graph, I think. Let's see if it's visible in Chrome. Okay, it's not visible in Chrome also. Okay, let's start our path from zero, current path zero, circuit this. Then we go to a edge. Similarly, we reach up to 2 and then go to 0 again. Okay, then we go to 0 now. Since 0 haven't got any unused edges, we put 0 in this circuit. Okay, means we need to use all the edges. It's about using the edges. Okay, not about the visiting the nodes. Okay, so we need to what we need to do. Okay, we have start node, and we need to transverse only that neighbors, which means the neighbors which edges are means not visited. So we need to mark the edges as the visited. So we need to keep track while creating a map. We can suppose we are creating a map from, suppose we have neighbors of 1 as the 3 and 2. Okay, so we can this means we have edge 1 3 and edge 1 2. Suppose we store a variable false here. This means this this edge is not visited, and for this edge also we can maintain a variable edges. In that way we can transfer all the edges, and we will also not get stuck into the cycle. Oh, and this will work for both cycles and circuits, means path and circuit, Euler path and circuit. Circuit contains cycle and path doesn't contain any cycle. So okay, so we need to, here in node data we have a neighbor. So along with the neighbor we need a boolean whether this edge is visited or not. So what we can do, we can create a pair here, pair, or let's say okay, pair. Yesterday yes, yesterday this I was not able to do this question. That question was that question was easy, but it took my a lot of time, so I was not able to do this question. But I have thought of a approach, its approach. We will discuss it first. We do this question. So we have this pair. So pair will have a neighbor list. Okay, nice. Acha. Let's call this V, and we need a boolean also. Boolean visited. But that was easy at the end. Means that was easy a lot. Let me show you my solution for that. This was the question. So now this will be our graph. So neighbor dot add with two, means we need to add a pair here in the neighbor now. That we will add v and a value false. Okay. That initially this is not visited, the neighbor is not visited. Yes, 3DDP. Okay, now in stack we can store integer. stack. This should be a stack. Okay, and what we can do, we can at the end print our stack system.out.println stack. Okay, and here we have this neighbor data, and in that neighbor data we have this will be our pair.v will be our next node, and visited will be this. And if our neighbor.visited, if it's already visited, then we will continue. Means this particular neighbor means this particular edge is already visited. Okay, we are getting error. So we are missing something. First is we don't need these braces, we need these braces. Okay, other is what error is this? Illegal start of this dot visited. V. Okay, instead of we need we are storing 2 here. Okay, this 2 edge. Okay, we have got error stack overflow. For this case. So what we are doing here, we have a map for this graph will look like from 1 to 2 and from 2 to 1 and from 3 to 2. So initially we start from 1, then we go to its neighbor. So 2 will be false. We get its neighbor data, this data, and we will transfer this data. Okay, we need to mark the neighbor as visited also if we once visit it. Okay. Okay, so in stack now we are getting 11, 9, 5, 4, 1 for this case, 1, 3, 2, 1 for this case. Okay, so I think This is not correct, I think. Means this will give us a pair 1 to 2, then 2 to 1, then 1 to 3. We don't have any pair. Okay, we have this pair. What's its output? 1 to 2, 2 to 1, 1. Okay. So I think we have solved this problem. So we just need to do is we need to remove from our stack and convert them into pairs. Means this particular part, what we need to do, we need to create our answer. So length of the answer will be like here we have 5 nodes and our answer has 4 nodes. So this will be a new int stack dot size minus 1 to 2. Okay. So we will pop from our stack while it's not empty. And we can get the current. Okay, what we can do, we can do stack dot pop, not pop, stack dot size is greater than 1. Okay, so our u will be stack dot pop and v will be stack dot peak. We have popped out this element 11 here, so this is 11 and this is peak. So we are not popping any element, we are just reading this element 9, so this will be 9 and we need to put 11 9 into our answer. So what we can do, we can put, okay, we also need index, so index will be 0 initially. So at index position, what we will put, at 0th position we will put u, and at 1 position we can put v. Okay, and suppose then what we can do, we will have this stack left after adding the first pair. So then what we will do next, we will pop out this element, so it will become 9. Now our stack has only these elements, so peak of this stack will be 4, so we will add 9 4. Then we have this particular part, uh, we will have this in the stack, so we will pull out 4. Now only 2 elements are remaining, we will peak will have this, so 4 and 5 will be our next pair. Then we will have this in our stack and we will pull out 4 and peak will be 1. Okay, so now we only have this element, so we will not proceed further. Okay, so at the end we can return answer. TP phone foundation. Okay, we need to implement it here only. Okay, Okay, we got TLE. Okay, we are visiting every node. Okay, I think need to resign it. How we can sign in into this? Okay, okay. Do we have? Let's use. I don't remember credentials for it. Maybe due to data structure. It's saying maybe due to data structure we have used, but we haven't used any inefficient data structure which can give us TLE. Don't maybe we have used. Sign up with Google. Nice. Okay, so I think we exactly need to implement this algorithm. We have wasted so much time on this problem and still not able to solve it. We are from 2 days stuck on this problem only. Need to solve DP problem also. Hmm, okay. What you are doing instead of marking this as visited, mm, we are using these two conditions. Okay, that our graph should contain this node. Okay, and graph the list is not empty. Instead of marking true, we are removing the nodes. That's the only difference I can see. And if we are removing, we can move this stack into the loop itself, because this will be means we only have a one order. This will return as a single way. Let's see if this works. And graph dot get start. This is our data, and in data we have this neighbor, and neighbor dot size is greater than 0. And what we are taking our next node, taking graph dot get dot start dot neighbor dot get. It's our last element. Means this size -1. Okay, means we can remove this instead of taking this, means so that we don't have to take it till next time. I'm passing that next here. Is it making any difference? Okay, so compilation error. Variable declaration not allowed here. Okay, wait a second. We have this part, and this is our node data. Okay, we have a pair. This is our pair. Let's say we need its v. Okay, okay. So this. Don't know how this algorithm is working and our was not working. Maybe removing while marking them, checking whether a neighbor is false or not. We were iterating this loop, so that is why we were getting, I think, TLE. Okay, so I think enough of lead code for today. So this was the approach to find Euler circuit or path in a graph. Okay, I think I can now sleep peacefully. Thank you, guys.